In the following examples, you can expect to see non-constant inner and outer radii, which means that we may see something like this: g1 of theta as a function for the inner curve. So this one for the inner curve or inner radius. And we may also see this g2 of theta as a function for the outer curve or outer radius. This one is outer. Now let's start with this example number 3. Here we are supposed to find the double integral of a multivariable function, and this function is equal to x. Even though this x is alone, this is actually a function of x and y. This one, x and y, but it's equal to x. And when you see x like this, you know right away this is in Cartesian form. And we are supposed to find the double integral over a domain region. So once again, we have this R, and it's going to be bounded by this curve and lines. So let's take a look at the first one. First one is x squared plus y squared equal to 2x. This one is interesting. It's a little bit more complicated than the one that we had before. The one that we had before is definitely a circle with radius 1, but with this, we don't know what kind of shape this one is. So next one is x equal to y. This one is simple, straight line. Next one is x-axis, also simple, and also equivalent to y equal to 0. Once again, we are going to start working on this example by plotting the domain region on a graph. So let's work it on this left-hand side. So right here, let's put a graph over here. Okay, so we have y-axis, okay, and x-axis, something like this. Okay, let's put label y and x, and we are going to try to plot all these curves and lines. And let's start with the first one. Here we have this x squared plus y squared equal to 2x, and we are supposed to plot this on the graph. But at this point, we don't know what kind of shape this one is, right? So let's put some work on this equation. Maybe it can come out to be something that we can visualize. So let's work on this equation right here. So let's put this x squared plus y squared equal to 2x. And let's do some moving things around. First of all, I am going to move 2x to the left-hand side. It's going to be minus 2x, and plus y squared still the same, right here. And now on the right-hand side, it's going to be equal to 0. The next thing I'm going to do is to plus 1 both sides, plus 1, plus 1. So everything stays the same. And now I am going to group this together. Alright, so in this group we have this parenthesis. We have x squared minus 2x plus 1, and we can do some factorization with this polynomial. And it should come out to be this x minus 1 squared, right, equal to that. And plus y squared still there, and this is equal to 1. At this point we have x term squared, right? We have x term squared plus y term squared equal to 1. This is definitely a circle of radius 1, right? But with this minus 1 right here inside the parenthesis, this circle is going to be shifted to the right 1 unit. So with this minus 1, the axis is going to get shifted, and we are going to get a circle shifted to the right 1 unit with the radius of 1. And it's going to look something like this. Okay, shifted 1 unit, so the center of this circle is going to be this point instead at 1. Okay, and we also have 2 right here. Now the center of this circle is going to be right here instead of the origin because of this shifting. Okay, now so we are going to put a circle of radius 1 to this point. Okay, so it should look something like this. I'm gonna try my best to make it a circle. Okay, so something like this, and lower part. Okay, so that is the first curve, a circle of radius 1 shifted to the right 1 unit. And now let's work on this. X equal to y, this one is simple, just straight line like that. And next one is x-axis, which is already there. So I'm going to highlight each one of them so that we can see the region trapped between them. So the first one is going to be x equal to y. Okay, this straight line. And next one is x-axis right here. And the last one is the circle of radius 1. It's going to be this. Okay, this curve. So there you go. We have this domain region for this double integral. Okay, this is the R that we need to perform the integration on. But just like in the last example, we notice that this shape is circular shape of R. So once again, we see that this is circular shape. Okay, so we see a circle right here. We are going to try the polar coordinate again. Okay, let's try polar form. Okay, so the first thing we are going to do is to work on the multivariable function. So let's start with the function right here, f of x, y. From the problem, we know that it's equal to x, and of course, we have to change this to be in terms of r and theta. So this is going to be, so let me write it right here. We want this. We want the function with r and theta instead of x because we want to work on the polar form. And just like in the last example, we know that x, we have this relation, right? X equal to r cosine theta. So that's why we have this right here. This function equal to r cosine theta. And there you go. We have this function in terms of r and theta ready to be used. Now we can try to construct the double integral right here. So it's going to be this double integral of this multivariable function in terms of r and theta. So it's going to be this r cosine theta with respect to differential area. dA is going to be r dr d theta. We already know that. Okay, so this one, you can make a note right here that dA, let's use, I'm going to put black right here, dA equal to r dr d theta. Okay, now the next job is to take a look at the details of the boundaries. So we have to take a look at the starting point of the radius sweeping and the end point of the radius, the outer curve, right? And starting point of the angle value and the end point of the angle value. Okay, why don't we start with the easier one? So let's start with the starting point of the angle. As you can see here, this line, the x-axis, represents theta equal to 0. So theta equal to 0 here. Easy. Now let's take a look at this one. This x equal to y, this line, this represents the angle of 45 degree, right? So 45 degree, it's pi over 4. Now, let's take a look at the radius, starting with the lower one, which is the inner curve, inner radius. So this one is inner. So we are going to take a look at the starting point of the sweeping of the radius. So it's going to start right here. And it's going to sweep from the inner curve to the outer curve. Something like this, right? So this one is inner curve. And we are going to copy that, replicate that over and over again until we cover the whole region right there. And as you can see, the starting point is always at the origin, which means that the radius is supposed to be 0 at the inner curve. So inner curve, inner point right here, radius equal to 0. No problem with that. Now, what about the outer curve? So the outer curve belongs to this curve right here. Let me highlight that. The question is the radius constant on this curve? It may seem to be constant because it's on the circle, right? But it's only constant when compared to the center of the circle. But if you compare it to this origin right here, let's take a look here. At this point, and when the theta equal to 0, and to this point, the radius is 2, right? Right across the circle. But once you move to this point along this curve to here, the radius, the distance from the origin to this point, is no longer 2. Okay? So this means that this r that we are looking at is not a constant. So you can highlight this again, and you can make a note that r is not constant. Outer radius, not constant. Outer r is not, well, you can say that not constant. Okay, not constant, which means that we are supposed to have a function to represent this outer curve, this one right here, and it's going to be g2 of theta. We need this g2 of theta to represent this curve. Okay, all right, so we need this r equal to g2 of theta. So this is outer one, not constant when compared to the origin. So we are going to have to do some work in order to find this g2 of theta. And as you can see here, this g2 of theta belongs to this circle, right? And it's going to belong to this equation right here. So we are going to make use of this equation to find this g2 of theta. And I'm going to work on this side. Okay, so let's make a note right here that, okay, we have observed that the outer r radius is not constant, which means that we are supposed to find this g2 of theta. Okay, now we are going to start with this equation right here. So this is the starting point. We start with this x squared plus y squared equal to 2x, and we want to transform this equation in Cartesian coordinate into polar form. So we are going to start with this x squared plus y squared, and when you see this, you think of the third relationship between Cartesian and polar, and that is x squared plus y squared equal to r squared. So this is going to become r squared. Alright, and 2 still the same, x equal to r cosine theta. So let's put everything here, r cosine theta. So there you go, everything is in r and theta. And we can cancel this square right here and this r right here. And in the end, we have this r equal to 2 cosine theta. This means that this radius is going to be equal to 2 cosine theta. And that's why we can assign this to function of g2 of theta. Okay? So we have it right here. g2 of theta is going to be equal to 2 cosine theta. And then we assign to the radius, the outer curve. Outer curve. Okay, now that we know about this g2 of theta, we got everything ready. So let's work on this double integral over here. So it's going to be this double integral, okay, of this r cosine theta. And since we have two r's right here, I'm going to combine them to r squared cosine theta dr d theta. And now the starting point of the radius in the curve is going to be 0 at the origin and ends at the curve that we just found, equal to g2 of theta, and that's equal to 2 cosine theta. So let's put it right here, 2 cosine theta. Now for the angle, starting at angle equal to 0 and ends at 45 degrees, pi over 4. Okay, so I'm going to integrate this with respect to r first. Once again, I'm going to work from the inside, integral. Okay, integrate with respect to r, and this is going to be equal to r to the r cubed over 3. Cosine theta stays the same, and I am supposed to evaluate this at two values of r. Okay, let me save some space. Okay, so this is equal to r cubed over 3 cosine theta, and I need to evaluate this at r equal to 0 and r equal to 2 cosine theta. And I'm supposed to integrate this again with respect to theta. Theta starting at 0 and ends at pi over 4. Now this 2 cosine theta has to go in. Let me fix this. 2. So this one has to go in as r right here. So once it goes in, it's going to be 8. Alright, cosine of theta cube times cosine theta. And we still have this 3 right here, which I don't like. What about I move this 1 over 3 outside of the integral? It's going to be easier. This one is going to get moved to the outside. Okay, so I'm going to put it right here, 1 over 3. Okay, so 1 over 3 is going to be outside. Okay, let me change this. Still outside. And we are supposed to integrate this, right, from 0 to pi over 4. Okay, back to the evaluation. Okay, 2 cosine theta already went in and we got this term. Now, r equal to 0 has to go in. Goes in here, it becomes 0. So we have this minus 0. We can just ignore that, right? So I'm going to put the end of this, this group right here. And we are supposed to integrate this with respect to theta. Okay, let me clean this up a little bit. I'm going to put 8 outside. This 8 is going to go outside of the integral. It's going to be 8 over 3. Right here we have this 8 over 3, and we still need to integrate this from theta equal to 0 to pi over 4. Okay, let me change color right here so you can see. Okay. The inside we have this cosine of theta, so 3 right here and 1 right here, it becomes 4 cosine theta to the 4th. Okay, and we need to integrate this with respect to theta. Now this one is going to be a little bit tricky, but it's still Cal 1 stuff. So in order to integrate this cosine to the power of 4, when you have this power 4 with trigonometry, it's a little bit hard to handle this. So with this, you can choose to use by parts to solve this. By parts, or you can try to simplify this term by using trigonometry property. Okay, trig properties. So 2 choices here. I'm going to pick with this trigonometry property first. Maybe I can make it more simple to solve. So I'm going to continue over here. Right? So having this cosine theta to the 4th is kind of hard to solve. What about I try to get rid of this power of 4? And there is a way to do that. So let's do it right here. Well, I can... What about I work right here? Let me put a line right here to separate. So we are going to start with the cosine theta square. So let's suppose that we have this cosine theta, okay, cosine of theta square, and we don't like this square because it's hard to integrate. So we can change this into a form without the power, and it's going to be this. We used this in the last example. It's going to be equal to 1 plus cosine 2 theta twice the angle over 2. So we have this relationship. And we want to try to use that to solve this cosine to the power of 4. So we are going to put this over here. We are going to square both sides of this equation. Alright. So for the left hand side, it's going to be this cosine of theta to the 4th. And let's see what we have on the right hand side. It's going to be 1 plus 2 front back, it's going to be 2 cosine of 2 theta, plus back square, it's going to be cosine of 2 theta to the 4th. And we have this 1 over 4, division by 4 right here, which I am going to separate to each of the terms. So it's going to be 4 over here, it's going to be 4 over here, and it's going to be 4 over here. Oh, by the way, this is supposed to be power of 2. I am sorry. So this is cosine of 2 theta square. Alright, now this one can cancel 2 and 4, so that the denominator becomes just 2. Okay, now this one is good, no power of 2 or 3. This one is also good, no power, but this one is not good yet because we still have this power of 2. So we have to come up with a way to get rid of this square right here. So from up here we can see that we can get rid of the square by doubling the angle, and we are going to do the same. So let me use green for that. So we have this term cosine of 2 theta square, which we want to get rid of this. So we are going to do the same as what we did up there. This is going to be equal to 1 plus cosine of double of the angle that we had before. Right? We have this 2 theta. So double the angle is going to be 4 theta. And it's going to be divided by 2. So there you go. So we can get rid of this square by using this term instead. And we are going to put this into cosine of 2 theta square. So in the end, let's see what we have. It's going to be cosine of theta to the 4th equal to first term 1 over 4 plus second term cosine of 2 theta over 2 plus this whole term goes in. So we have this 1 plus cosine of 4 theta divided by 2 and then divided by 4 again. Okay, we still have this 4, so don't forget that. So this, okay, we can combine them to make it 8. Alright, so in the end we have this. I am going to combine the constant 1 over 4 and 1 over 8, so it's going to be 3 over 8 plus cosine 2 theta, this is good, power of 1, plus cosine of 4 theta divided by 8, and that's equal to cosine of theta to the 4th. I don't like this, and now I got rid of it. So I am going to put all that I have right here, everything here, okay, into this right here, cosine theta to the 4th. So let's do that over here. This is going to be equal to 8 over 3 still here, integration of, okay, whole terms goes in, so we have this 3 over 8 plus cosine of 2 theta over 2 plus cosine of 4 theta over 8, 4 theta over 8, and we are supposed to integrate this with respect to theta. Okay, so let me put a wall right here, boundary. Okay, and we are supposed to integrate from theta equal to 0 to theta equal to pi over 4. And this, okay, sorry about that. This is supposed to be equal to, okay, let's integrate each term of this. So first one, right here, it's going to be equal to 3 over 8 theta. Okay, now let's integrate this. Integrate cosine of 2 theta. Integrate cosine, you get sine of 2 theta. But with this 2 right here, it's going to get divided with the reverse chain rule. So it's going to be sine 2 theta over 2. With this remaining 2, it becomes sine 2 theta over 4. So this is going to be sine 2 theta over 2 times 2, it becomes 4. Plus, I need to integrate this with respect to theta. I get sine 4 theta over 4. But with this remaining 8, so it's going to be sine 4 theta over 4 times 8, it becomes 32. And there you go. We are supposed to evaluate this at 0. Theta is 0 and theta equal to pi over 4. But before anything, let me multiply this 8 in. This 8 is going to go in, cancel with this. Okay, gone. cancel with this, and I get 2 right here instead. Alright, 2 right here. And cancel with this, and I get 4. Okay, this becomes 4. Okay, what about I use this red right here, 4, and this is 2. Okay, now we are supposed to put pi over 4 in. Let's do that. 1 over 3 still remaining right here. So here we have this 3, pi over 4 goes in right here and here and here. So let's find out about that. 3. Okay, we run out of space, so I'm going to shift this up a little bit. Equal to 1 over 3. First term, 3 is still there. Theta as pi over 4. So we have this pi over 4. Plus 2 sine of 2 theta. Theta equal to pi over 4. This is sine of pi over 2. Okay? And that's it for the second term. Next term, sine of 4 theta. This one, theta equal to pi over 4. So it's going to be sine of pi. Alright? And divided by 4. Let's move 0 over here. And that is the first term. Okay, and we are supposed to minus with the second term, which means that I'm supposed to put the bigger parenthesis over here. Okay, 0 goes in. 0, this one, theta equal to 0 goes in here, here, and here. So first term, 0 goes in, of course it has to be 0. Second term, 0 goes in, it's going to be sine 0. Sine 0 is 0. And 0 goes in here again. Sine of 4 times 0, still sine 0. So you get this 0. So definitely the whole term is 0. So you don't need to worry about this. Okay? And this one, sine pi, you also know that this is equal to 0. Okay. So in the end, we only have these two terms left. Equal to 1 over 3 times 3 pi over 4. And this sine pi over 2 is equal to 1. So we have plus 2 right here. And this is going to come out to be equal to pi over 4 plus 2 over 3 as the answer for this example. Okay, now let's move to example number 4. In this example, we have a double integral again, and we see this x and y, so we know it's Cartesian. Alright, so we see this, we know it's Cartesian. And we don't need to find out about the integration domain because it's given to us. So let's take a look here. By the way, when you see this order, dy dx, and do you see something like this, you know right away this is type 1. Type 1 rectangular domain. Okay, and let's take a look here. Since we integrate with respect to y first, so here with respect to y first, the value right here is going to belong to y. Y equal to 0, which is the lower curve. Oh, by the way, type 1, to remind you, for this type we have this lower and upper curve. Alright, so we already see this y equal to 0 as the lower curve, and this one up here as the upper curve, y equal to square root of 1 minus x minus 1 squared. And let me fix this. This is supposed to be y. And then after we integrate with respect to y, we get this integration with respect to x. So this 0 right here belongs to x. So this is supposed to be x equal to 0, starting point of the x value. And x ends at 2. Okay, once again, first thing we are supposed to do is to draw this domain region in the graph. So I'm going to use this information that I have right here to draw a integration domain right here. So it's going to be this y-axis again and x-axis right here. So let's take a look at the information that we have. We have this y equal to 0. Okay, that is x-axis. No surprise there. This one is x-axis. Make a note here that this is x-axis. And next one is going to be this y equal to square root of 1 minus x minus 1 square. And also make a note right here that this x-axis is supposed to be lower curve. This one is supposed to be the lower curve, right? Because in type 1 we always start sweeping from the lower curve to the upper curve. Okay, so this second one is the upper curve. And we are supposed to draw them on the graph. Okay, this is y and this is x. This one is easy because this is x-axis is already in there. But this one not so much. We don't know what that looks like. So let's try to put some work into this. So this one I'm going to square both sides. It's going to be y squared equal to 1 minus x minus 1 square. Alright, what about I move things around and I get this. Move things around, I get this x minus 1 square plus y square equal to 1. And there you go, we have the same equation that we had in example 3. So make a note here that this one is the same circle as in example 3. It's going to be a circle with radius of 1 and it gets shifted to the right 1 unit. So there you go. With this information right here, we put some work and we get this curve out. It's going to look the same, like this. Origin at 1, 0. Maybe somewhere around here. And this is 2. Okay, 1 and 2. Okay, and it should be something like this. Okay, let's assume that this is a circle. Okay, so this is the curve that we need, alright, and let's do some sweeping. So let's take a look at the meaning of this. We are going to sweep from the lower curve, this one lower curve, which is the x-axis, to the upper curve, which is this curve right here, this circle right here. So we are going to sweep from the lower curve, which is this lower curve, x-axis, to the upper curve of this circle. So we are looking at this region right here. So it's going to be this sweeping lower curve to the upper. Alright. Now let's take a look at the range of the x variable. X start at 0, ends at 2. So x start at 0 right here and ends at 2. Okay, so this is the whole half the circle that we need to consider. So there you go, we have this domain region in this problem. Half a circle. Okay, so the next thing that we see that is this one is a circular shape. Once again, we notice that this one is circular shape. Once again, circular shape. And we see this circular. Then we want to try to use the polar form for the double integration. Polar form. Okay, so, and now it's going to be a repeat of everything again. We are going to start with the multivariable function, f of xy. Let's see what we have here. F of xy, we have this x plus y over x squared plus y squared. And we are supposed to transform this into a multivariable function in terms of radius and theta. So let's do that right here. Okay, so we want this so that we can build the double integral in terms of r and theta. R and theta. It's going to be equal to, alright, let's start with this one. This one is easy. From the third relationship, it's going to be equal to r squared. This one equal to r squared. So that's why we have this. Okay. R squared down here. This x is going to be equal to r cosine theta. Let me put the relationship right here. Okay, x equal to r cosine theta, and y equal to r sine theta. Okay, and up here we are going to get this r cosine theta plus r sine theta. And as you can see, we can cancel this r and r right here. And in the end, we have this. Okay. In the end, we have this 1 over r and cosine, let me put this sine theta first. Sine theta plus cosine theta. Okay, that is the function in terms of radius and angle. And that's what we need in the double integral in polar form. Okay, now that we have this, we are supposed to construct the double integral right here. So it's going to be over here, double integral of this multivariable function. It's going to be, I'm going to put the whole thing right here, 1 over r, okay, of sine theta plus cosine theta, and with respect to differential area, r dr d theta, which is good because this r can cancel with this one, can cancel with this. Now we are supposed to find all of these information, starting of the sweeping of the radius and ending point. So inner curve and the outer curve, and then we also have this starting point for the theta and end point for the theta. So let's start with the easier one again. So starting point of the angle is going to be this. Okay, it's going to be this x-axis. Once again, it's going to be theta equal to 0. Okay, so this is going to be equal to 0. And the end point of this sweeping is going to go up like this, sweep theta until we reach the pi over 2. So theta ends at pi over 2, 90 degrees, equal to pi over 2. Now, what about the inner curve when it comes to the radius, inner radius? As you can see, the sweeping starts, what about I use black? Okay, sweeping start at this point at the origin, and we are going to sweep from the inner curve to the outer curve. As you can see here, inner curve to the outer curve, and we are going to repeat this again and again until we cover the whole region, right? And as you can see, the starting of the sweeping of the radius always start at the origin, which means that the inner curve is radius equal to 0. So here we have this r equal to 0 as the inner curve. Once again, this is inner curve. Okay, what about the outer curve? As you can see here, the outside of this curve is going to belong to this circle. Okay, so outer curve belongs to this circle right here. And we need to find this g2 of theta for this curve. And since it's the same circle as the last example, once again, this is the same circle as the last example, g2 of theta is going to be the same as well. So we are going to bring this back from the last example. g2 of theta is going to be equal to 2 cosine theta again. So let's use this. So this one is going to be r equal to 2 cosine theta. Once again, this is outer, and you can make a note that this is the same as, okay, this one, same as example 3. Okay. Now let's proceed to work on this integral. So we are going to start from the inside to outside. So we are going to start with this, right? Integrate this with respect to r first, and then we do that with respect to theta later. So we are going to integrate this with respect to r, and we get this r of this constant sine theta plus cosine theta. So nothing fancy. You integrate a constant like this, you get an extra r right here. And we are supposed to evaluate this at two values of r equal to 0 and r equal to 2 cosine theta. and we are supposed to integrate this with respect to theta again. So theta starts at 0 and ends at pi over 2. Okay, so this has to go in. This one has to go in here. Alright, right here. So this is going to be equal to integrate of 0 to 2 of pi over 2, and r equal to 2 cosine theta goes in. We have this 2 cosine theta times this whole term, sine theta plus cosine theta. Okay, now this 0 goes in. 0, this one goes in here, everything is going to go to 0, right? So we don't need to worry about that term. And we are supposed to integrate this with respect to theta. So this is going to be the same, equal to integration from theta equal to 0 to pi over 2. And the inside we have this 2 sine theta times cosine theta plus 2 cosine theta squared. Alright, and we are supposed to integrate this with respect to theta. And as you can see here, we see these two terms. First of all, a product of a sine theta and cosine theta. And second one is this cosine theta square with this square right here. Not going to be easy to integrate this directly, so we are going to use trigonometry properties again. Trig property again. So this 2 cosine theta, sine theta is going to be equal to sine 2 theta. Alright? Same thing as what we had before. And this cosine theta square, it's going to be equal to 1 plus cosine 2 theta over 2. Okay, with these terms, it's going to become more simple and easier to solve. So here, this is going to be equal to integrate of sine 2 theta plus, okay, we have this 2 right here. It's going to cancel with this 2 right here. So this is going to be 1 plus cosine of 2 theta. Oh, by the way, this is supposed to be s. Okay, and we are supposed to integrate this with respect to theta. Theta from 0 to pi over 2. Okay, let's integrate the first term. Integrate sine 2 theta, you get minus cosine 2 theta over 2. So here we get minus cosine 2 theta over 2. Integrate 1, you get theta. Integrate cosine 2 theta, you get sine 2 theta over 2. And we are supposed to evaluate this at 0 and pi over 2. So this is equal to minus cosine of pi, okay, over 2 plus pi over 2 plus sine of pi over 2. First term minus second term, 0 goes in, minus cosine 0 over 2 plus 0 plus sine of 0 over 2. Okay, let's take a look at each one of them. Okay, cosine of pi is going to be equal to minus 1. So the first term, I'm sorry about the space, I need to put it right here. Equal to, first term equal to 1 over 2. Okay? Alright, now second term is going to be equal to this pi over 2 right here. Plus pi over 2. Sine pi is going to be equal to 0. No problem with that. Sine 0 right here goes to 0. Same thing here, 0. This cosine 0 is going to be equal to 1. So this is going to be equal to plus 1 over 2. So in the end, we have this 1 plus pi over 2 as the answer for this example right here. Let me put a box around that because it's quite messy around here. So that is the answer for this one.